Hello and welcome. Gas dynamics, the engineering of high-speed flows, is covered in chapter 15. Gases use the perfect gas model for simplicity, and there are new kinds of properties, lots of types of properties that appear in gas dynamics. And in fact, the mass, energy, and entropy equation are recast in the form of total properties, critical properties, etc. With the help of those equations, we'll try to understand what is isentropic flow, and some examples of normal and oblique shocks, expansion waves, etc. But at the end, we want to solve a fairly complicated problem like this, where we have a gas, say air, in a reservoir at 1000 kPa, 1000 Kelvin, and it's rushing out through a nozzle. Only a symmetric half is shown here, and it goes through a throat, and then there is a normal shock that stands at a location where the area is twice that of throat area, and we are asked to find, say, the mass flow rate and exit velocity and all the other information about this nozzle. That's quite an undertaking. So let's start with a few animation first, but before we go there, let's make the first one. Okay, so as you can see, the different kind of properties are described in this animation: static and total properties, what is critical area, etc. Here is an animation showing what is the speed of sound, which plays a very important role because velocity is non-dimensionalized or normalized by velocity of sound. It appears as a natural variable everywhere. Here is an example of how the equation simplifies for an isentropic flow. Entropy remains constant, but in gas dynamics terms, it becomes total property remain constant, for instance. Energy equation becomes total temperature remains constant. Mass equation becomes critical area becomes constant. So this will be our counterpart of mass, energy, and entropy equation, which leads to this equation. These are called gas dynamics isentropic equations, which, if you know the local Mach number, you can solve for local properties. In this animation, it shows what is a normal shock, how it is created by aggregation or coagulation of sound waves. Essentially, here is an example of an oblique shock. In this example, in this animation, what is shown is the equations for how to handle a normal shock wave. Obviously, a shock wave has a lot of thermodynamic friction inside, so it's not isentropic. Important thing to understand is that there is a drop of total pressure across a normal shock wave, but the total temperature across a shock wave remains constant. Okay, finally, the test step for gas dynamics is quite sophisticated, much beyond what an undergraduate thermodynamics book covers. You can use that to analyze a complicated flow structure involving expansion fan and oblique shock waves that you see at the jet of a military jet, for instance. So now that I've gone over the breadth of gas dynamics, let's first mention that before you launch any test step or gas dynamics test step, you make sure that you are very familiar with how to evaluate properties, especially the PG model, because air or any other gas is treated by perfect gas model in gas dynamics. Understanding of open steady device analysis also is going to be very helpful. So let's go and launch the gas dynamics test step. Again, you follow the system, open system, and the specific branch, and you will see the gas dynamics app right here. There are some examples here, but the state panel is going to look very similar to the perfect gas model state panel, except it has new properties such as the total temperature here, total pressure here, critical area, which is S star, and the Mach number. Also, if you go to the gas dynamics tables panel, this is the new panel, you'll see that this is the isentropic table. So suppose a Mach number is given to you. Well, first you have to select a gas. So to select a gas, you select the gas and calculate any state. Just click the calculate button. Now if we enter the Mach number, things will work. So for instance, Mach number is 2, isentropic table is calculated, the local static to total properties. You don't have to know the Mach number. Suppose you know the pressure ratio, then it will calculate all other variables. So that saves you time from looking up an isentropic table. Normal shock table, similarly, suppose Mach number is 2, you can calculate all the other ratios across the shock wave. Obviously, after the shock wave, the Mach number is less than 1. Instead of knowing the Mach number, suppose you know the total pressure temperature ratio, for instance, it will find the Mach number. Similarly, there are, this is for oblique shock, delta theta. If you expand the table, suppose again, we have a Mach number of 2 coming in and the flow is turned around by an angle, let's say 10 degree, then you can calculate what should be theta, the oblique shock angle. For Prandtl-Meyer expansion table, similarly, suppose Mach number is again, let's 2, and we'll calculate the mu and nu, the two angles that's necessary to understand the expansion fan. So now let's get back to the problem at hand. The problem that we want to solve has been shown in this PowerPoint. I have already solved the problem, so I'll just walk you over what I have done for the sake of time. First of all, as you can see, state 0 is set as the stagnation state or the total state in the reservoir. 1000 kPa is given to us. Also is given is the temperature is given. And we'll set velocity to 0 because it's a stagnation chamber. Inside the chamber, there is no flow. So the local temperature, the temperature and pressure act as the total temperature and pressure in an isentropic flow. As we go along, as we move along, this must be the total temperature and pressure. So state 1 is our throat state. Throat meaning where the nozzle is restricted to its lowest area. And in the throat, the information given are, the area is given to us 10 centimeters square. And we do know that the energy equation means total temperature doesn't change. Total temperature is set to equals T0. Total pressure, that's counterpart on entropy equation. And at the throat, we do know that Mach number becomes 1 in an isentropic flow if because the shock wave is standing, we know that at the throat there must be Mach number equals 1. It's not necessary if the back pressure is low enough or high enough, there may not be a supersonic flow. There may not be a Mach number 1 at the throat. But right now we know there is a shock standing downstream, which immediately means the flow must be supersonic from state 1 to state 2. 2 and 3 are the states right before and after the shock. So given this information, everything else is calculated. The mass flow rate through the nozzle must be always this. So it's important to understand that the continuity of mass must be satisfied throughout the nozzle, obviously. So this is something to keep an eye on. So state 2 is what? Is an isentropic state right until the shock wave. So for state 2 again, we know the area is given to us. Area is twice that of throat area, and it's isentropic. Therefore, energy equation tells us always for every flow, the energy actually is the total temperature remain constant because it's isentropic flow. Entropy remain constant, and the counterpart for that is total pressure. Finally, mass flow rate is constant becomes A star remains constant. As we calculate, you notice that as we calculate, keep an eye on this help area. This is our help area. Recall. So if we go and put the pointer over the Mach number, you'll see the Mach number is shown to be whatever it is, 0.3059, but an alternative supersonic solution is shown, 2.197. That you got to understand. Because the area A star and A are given in this problem, their area ratio, as you know, will produce two solutions, one subsonic, one supersonic. So we know in this case we must pick the supersonic solution, otherwise there will be no shock wave. So what we do, we say, okay, A star is not known, instead the Mach number is known. So we introduce the supersonic solution that we already found, 2.197. 7. So now S star will be still same as S star 1. M dot 2 will be same as M dot 1, almost equal as you can see. But the solution is now supersonic. So at the throat, the velocity is very high now, 993 meter per second. Okay, so how do we find the state right after the shock? Mach number is given, so we can go to the table and put the Mach number here in the normal shock table. That gives us the exit Mach number. So 0.547 should be the Mach number at state 3, and that's what I've substituted here. So we know the Mach number, we also know the total temperature doesn't change, and of course the area barely changes across the shock. Shock is so thin, A3 and A2 must be equal. And we need one more information, and the pressure ratio we know has decreased across the shock, the total pressure ratio. So you can find in the shock table that we just covered that if you go back to the shock table, you will see that the pressure ratio is given here, PT E over PTI is 0.629. We come back, that's what we have substituted here. So therefore, state 3 is completely evaluated. Again, the mass flow rate must be the same as m dot 2, m dot 1, etc. Finally, to get the final state, we go to state 4. And what do we know there? Again, the area is given, 4 times the throat area. Total temperature must be, actually we could set that to T0, it never changes. But total pressure is set to PT3, the state after the shock, because the flow is isentropic from the state after the shock until the exit. So as you can see, similarly S star 4 must be equal to S star 3. So this is just an isentropic solution from state 3 to 4, and that produces the final velocity to be 149 meter per second. As you can understand, it's way lower than the higher speed obtained. State 2 probably will have our highest speed because that's the supersonic. State 2 has a speed of 993 meter per second before the shock reduces the speed to 336, and the diffuser, it works, the diverging section works like a diffuser, bringing the velocity down to 149. So well, I'm going into too much details for this problem, for this particular problem, but I just wanted to show you how powerful this is. So if you want to know how much entropy is generated, we could, of course, isentropic except between, say, state 3 and state 4, you can calculate, and you'll see entropy generation rate is calculated here. Heat transfer is 0, W dot external equals 0. So yes, a super calculator as usual will produce a detailed report and the test code from which you can readily regenerate the solution.